Okay, so this is our theorem 11. So after this, I will kind of get into the specific construction for our sort of algorithm C++ code for this. So it's a bit more concrete. So the VC inequality is of this form. The expectation of the supremum over A so this is less than or equal to 2 times the square root of the natural logarithm 2, and this quantity called S script A of n, define this in a sec, over n. Okay. So what is S subscript A of n? This is called, this is actually the maximum of n points, lowercase x1 through xn. So these are just deterministic points in Rd. So you have n points in Rd, each one. And what you're after is the cardinality or the size of the set x1, x2, up through xn. So we take this n-point set, right, n points in Rd. We take that set and we intersect it with NA, and then we let the A vary over the class A. And it's the size of this, right? It's the maximum size of this. And this is called the shatter coefficient. This is called the Vapnik-Chervonenkis shatter coefficient. So in English, this just gives us the maximal number of different or distinct subsets of a set of n points that can be obtained from obtained by intersecting eight elements of it. So, right. So how many ways can we shatter or break this n-point sets by intersecting it with sets from the collection? So that's essentially the fundamental quantity that controls this, the expected supremal deviation of the empirical measure from the true measure over some collection A is completely controlled by the shatter coefficient of A. So
but this is now for fixed A again, right?
Yeah, this is for fixed collection A. Yeah. I mean, this collection is general. It doesn't have to be finite anymore. That's what our basic generalization is, right? So we don't have to stick to this. MDE can work for, more general finite setting.
Is this intersection with A? Is that over all A in script day, or is it
for each? So you can think of it as so you can think of okay, maybe this is Luke's notation. So I think in our notation we did this, right? So you think of this as the set of all xn's intersected with A for each A in A, and this will produce. So because this is some set, and when this intersects with this, it's going to produce. If it contains everything, it'll produce the whole set. If it only intersects some of the xi's, it'll produce a subset. So this whole thing is going to produce various subsets of x1 through xn at the end, because we are allowing capital A to march through script A, right?
Do you mean this intersection is non-empty or?
No.
Huh?
So what this? I mean, this set of such sets, it can't be bigger than A, because and it can't be bigger than 2 to the n.
Yeah.
So this white cannot be more than 2 to the n.
Because because it's also a subset of x1, x2, x3, x4, x5 up to xn, right? Each subset is also a subset of this finite set, so it can at most be the size of the power set.
Okay.
Yeah, I mean, it's upper bounded by the power set of x to the n.
Okay.
But this could be a count, this could be
exactly
an infinite collection. So
and this can be finite even if this is an infinite. So this is the point.
Okay, so and if there are two sets A and A prime in script A such that the intersection with the xn's produce the same subset, say x1 and x2, then the outer set makes it distinct, so we don't care. So we don't really care if two sets in script A, produce the same subset of the endpoint set. Then they
So it's a bit like looking at the set script A at a lower resolution somehow.
Yes, exactly. So we are, and remember, this is completely arbitrary. So I'm allowed to change the endpoint set in RD completely arbitrarily. So it's for everything I get that, and so I find the maximum cardinality, which will be some number smaller than or equal to 2 to the n, by varying this endpoints deterministically in RD. Okay, so that's the shatter coefficient. So then if you do the proof, this is due to Genet and Zinn and Hessengerbaum. Okay, so what we're going to do is first introduce copies, x1 prime up through xn prime as independent copy of x1 to xn. So now we're going to have sigma 1 through sigma n as n IID variables for signs. I call it sign variables. With probability of sigma equals -1 is equal to the probability of sigma equaling +1 is equal to half. So we toss a fair coin and get the signs. These are also independent of both the x and its copy. So then we're going to have a empirical measure of the copy. U sub n prime of A is 1 over n, summation as I goes from 1 through n. Right? So when it's done, then the expectation of the supremum of mu n of A minus mu of A is going to equal the expectation of the supremum of A given x1 through xn. So now I want to use Jensen's inequality and say the expectation is supremum is the expectation of the absolute value of mu n of A minus mu n prime of A given and convexity. Of absolute value. So then this is less than or equal to the expectation of the supremum so why? Because the supremum of the expectation is less than the expectation of the supremum, and the expectation of something given something is equal to the expectation of first thing. So this gives me 1 over n and the expectation, the supremum of A, absolute value. Now I plug in my sigma i's. Okay, and absolute value. Okay. So
the sigma is just because xi and x prime I have the same distribution.
yeah. And this is my, and also let's note that this is because x1, x1 prime, and x2, x2 prime, all the way to xn, xn prime are ID.
Yeah.
And then this is 1 over n. Expectation of the expectation of the supremum of A and A of the absolute value of the summation times the indicator function of xi and A minus the indicator function of xi prime. And this is now conditional. So this is the absolute value, and this is now conditional on all my x1, x1 prime, and so on up to xn, xn prime. Okay, I close my outer inner expectation and my outer. Sorry, it's a bit cramped here. Okay, so I'm just using these. So this copying argument kind of pretty much it sort of pops everywhere. I don't know whose idea originally this was.
I think it might go back to writing the variance as the expected difference between two, or something like this.
Oh,
this is a very old idea.
Yeah, yeah, true. So now let's so since the sigma i's assigns are independent of all these guys, the x's and their copies, let us fix x1 to be a realization, these lowercase guys, and investigate the following. The expectation of the supremum of the absolute value of the indicator function okay, so sorry, this is lowercase x. So then let A hat script A hat be a subset of script A, but this script A hat be a collection of sets such that any two sets in script A hat have different intersections. with our set x1, x1 prime, all the way to xn, these two endpoints. Okay, that I can do, right? I'm not telling you how you pick, but you can pick this. So then, we also mandate that every possible intersection is represented once. So together, the size of script A hat is going to be less than or equal to our shadow coefficient of two endpoints. And the expectation supremum only of the absolute value of sigma r and of the indicator function xi a minus the indicator function of xi prime a is simply going to be equal to the expectation of the maximum of A in script A hat of the quantity I going from 1 to n of sigma r times the thing. I just moved to a finite setting. That's all I've done. Okay. And we are almost at the end of this group. So let's leave this guy.
This is because this just depends on which ±1 pattern you get from the indicators, and
yeah,
this the pattern that maximizes it will appear for some A and A.
Yes, I think that's what I'm about to. Right. Yeah.
Oh, sorry.
No,
I keep preempting you.
it's good. You know, it should be. Yeah. So basically. So each sigma I, right, this is what you mean, minus so this sigma I, because of these guys being copies, this has mean 0. And I think, yeah, I think what you're telling Tilo is for understanding that the supremum becomes maximum.
Yeah, exactly.
Yeah. Okay, so this is, you know what, I do this one this way, and then you know where I get this one from?
I see.
It's the German one, you know. Anyway, it's kind of messed up. Okay. Yeah.
You got the German one from the German one.
Yeah. I got those German ones that pop randomly. And so anyway, my lemma for we have, right, so remember lemma 4 was our upper bounding MGFT. Only generating function upper bound random variable. So we have for any s greater than 0, the expectation of e to the s summation as I goes from 1 through n of sigma sub I of the indicator of xi in A minus the indicator of xi prime in A. This is simply going to be the product of okay, and this thing is less than or equal to the product as I goes from 1 to n of e to the s squared 2 squared over 8. Okay, so this is e to the n squared over 2. And this is because the distribution of sigma I this quantity upstairs is symmetric. Because of the Bernoulli sigmas. So finally, with lemma 6, we have 2 more lines, and we are done with the first Bayesian inequality. So now lemma 6, this is the expected maximal deviation inequality. This implies that the maximum over A in A tilde summed over 1 through n okay, so sigma of this, the value of this event is less than or equal to square root of 2n log 2 times the shatter coefficient of 2n. Okay, and this is less than or equal to the square root of 2n log 2 squared. Okay. since F2n is smaller than S script A of n squared. So now by dividing by n, or dividing by 1 over n on both sides, we get our initial inequality.
So why do you want the n squared rather than 2n?
Because I think we just want to get this theorem. This is how it's stated.
Would the theorem be much stronger with 2n rather than n squared?
Yeah.
Oh well, maybe we'll see later.
Yeah. I mean, oh wait, sorry, what am I? Oh wait. Sorry, the square is outside.
Okay.
Sorry. Yes, I mean this is loose, but
Yeah, this
sorry, that was
this is much.
Yeah.
This bothers me much less.
yeah. No, good question. I was sloppy. I did it correctly here.
Okay.
So yeah.
Okay.
So what we want is yeah, well, we're done basically. So then putting this all together basically is the expectation of the supremum of A in script A of the empirical measure minus the true measure is less than or equal to 2 times square root of log 2 SA of n. Okay. So that's oh good. We have a little time for some actual coding. So I'll show you some actual constructions because this is quite generic and high level. I mean, it's fine. It's a very general machinery. So now the program is, of course, you know, I have gone through maybe what I think the fastest, most interesting path through this book. This is full of information. It's very dense. So I've just mostly jumped around several chapters here. What I think we can maybe...
One quick question. Sure. If the true process were a Cauchy process, would everything fall apart then?
So if you have a Cauchy density, right?
Yeah.
So is Cauchy density in L1? I mean, Cauchy density, it's just that expectation doesn't exist,
Yeah.
right?
Yeah.
But it's still a density.
Yeah.
So you can, you know, it integrates to 1.
Yeah.
It lives in L1.
Yeah.
No, the theory will.
But sort of the MGF, I mean, I'm a bit vague, but would that exist for Cauchy density?
Which one?
The MGF, the moment generating function.
Well,
So we never use the moment generating function of the underlying
density.
density.
Ah, okay, yeah.
It's
We
just
only
of all
use-
these sums of indicators and
Yeah.
things.
Okay. But we'll never find it. I mean, if we had a Cauchy in our G, right, we could investigate it. Then we would have it there.
Well, the problem with Cauchy is something else, which
So maybe so one thing to clarify, because this is again this very tricky thing with the structure of the underlying space and the structure of the measures, the probability distributions on this space. Because I think there's nothing here that sort of the distribution doesn't really have to be Euclidean. Right? These x's or distributions could be on any space. It could be just, I mean, Psi likes graphs. This could be some distributions of on graphs.
well, I don't know, because the shadow coefficient is really explicitly defined on. Well, then you have to generalize what is an endpoint set.
Yeah, you have your underlying space, and you have endpoints in the space, right?
So each point is what? No.
Any sample in the space where your distribution lives.
I mean, as far as I understand, all of this we've developed is for points in RD, and my density estimate is defined as a mapping from R, what is it? RD to the n+1 to R, right? So it takes in all the data and then produces some mapping from RD to R.
Maybe we have something hidden somewhere, but I don't. So maybe I'm just being overly optimistic or something, but I don't remember us ever using the fact that we were on a.
But we explicitly state that the Cherv coefficient is
Yeah,
defined.
Yeah, but you could just replace
Could
RD.
we replace that in
exactly.
some meaningful sense?
I mean, you just replace RD, but whatever you like, right?
Well, I don't know. I'm not like this comfortable with this theory. Like I don't, because let's look at the coalescent realizations of the n-coalescent, Kingman's coalescent. We did this yesterday, right? So you have some topologies and you have branch links. So they're trees, they're very well defined, and there is a very clear measure on this. And there are parametric families of coalescents. So we study something called a beta coalescent. So for a given parameter beta, the topology changes. It has a different distribution on tree topologies, and the branch lengths could be the same. For example, it could be exponentially distributed for each epoch at some rate. Okay. So I don't know if a point in a space is a coalescent tree, and you have realizations of coalescent trees.
I mean, you just look at sets of n coalescent trees, and then you look at how many ways you can shatter these set of trees using the Yatrikas.
Yeah, but I'm saying for trees, intersections are.
No, you're just intersecting sets. You're never intersecting. You're not intersecting points in Euclidean space here either.
Right. So then I need somehow a collection of sets of trees that are in my sort of.
Yeah, but so if you have a reference measure, so say that you have a uniform, you bound this to some small set of trees.
Okay.
You take a uniform measure on this set. I mean, this is, I guess, a countable set, so it's no problem to find some distribution on it. And then you define the density with respect to this. I mean, this is just probability mass function instead, and you can still do all that. I think on trees and graphs, it's probably not interesting because it's finite spaces, so it doesn't give you that much. But you could, as far as I can tell, you can have any.
Yeah, so
I mean, it might be very hard to work with theoretically to do anything with this, but I don't think this ever sort of. I don't think we ever explicitly use the fact that we're on a Euclidean space. Which means, and the Cauchy, the problem with the Cauchy distribution with the tails, this is explicitly sort of related to the distance, to the notions of distance on Euclidean space. So if this doesn't depend on your notion of distance in Euclidean space, then it can't be a problem to have a Cauchy distribution because it can't actually, it doesn't feel distances. This doesn't see distances.
Yeah, I have to really think about this. I never really thought about MDE in like. I work on tree space all the time, but I never really thought about it. But yeah,
but you're not trying to estimate an unknown distribution on trees either.
No, that is exactly the genome scan problem.
Okay.
So we're doing it, but in this other semi-parametric way. I kind of work, but I should think about it more. Actually, it's a good idea. I might never leave the MGU world. All right, let me show you some actual algorithms and codes quickly before we.
Let me just turn back the settings too.
So if anyone wants to go for a pint beer or something, I might buy some first round or something.
What's up with your touchpad? No, I finally managed to.
So what I presented is very, very generic, and that's good. So now we want to specialize it quite a bit. So
I mean, in practice, you'll probably want, constructing these Yatrikas classes, where the densities are bigger and smaller. I mean, this will probably quickly become quite unnatural, because, if you have something like Gaussian on Euclidean space, then you have a notion of continuity, and you can just sort of find the points where they intersect and sort of look at where all the tops go. If you have some very abstract space, where you don't understand the structure of the space even, then looking at where various densities are sort of bigger than smaller on the space where you don't understand the space itself will probably very quickly become hard.
And the implementation actually requires you to construct these.
Yes, exactly. I mean, to actually understand how big this upper bound here is, you need to understand how complicated this set is. And looking at sets of subsets of something, if you don't understand even basic structure of this thing, then looking at classes of subsets of this thing will be even harder.
So I'll show you concretely. It's so there's a few more things we need. Okay, so I haven't really prepared. I didn't think I'll get this far today.
So another more general question. Say a non-stationary random variable. I mean that sort of growing. Would that work? How would that sort of? What would happen? I mean, you can't really estimate the density for it.
I mean, so now you're talking about like some sort of non-stationary process. That's
how would this? I'm just.
So,
I mean, what are you trying to estimate?
The density of it, basically. But I guess it wouldn't exist density. Maybe I'm getting tired.
I mean, the density of because if you want to be able to estimate,
would be sort of. I mean, a random walk, say.
Yeah.
The moments would be indefinite, right?
Yeah. But I mean, then are you trying to estimate the density on the set of possible paths?
No, if I have a realization of it, I have sort of.
But you don't have a lot of samples then, right? Because if it's not stationary and things change with time, you just have one sample for every time point. So you're not getting more and more samples of one density. You're getting one sample for lots of different densities.
Yes. Okay. Yeah, but I mean the problem. I mean it wouldn't work on. I mean if you have a growing time series, you wouldn't make sense of it.
But you might be able to do something if you get multiple realizations from the same non-stationary thing. But so if you're able to restart it and do it over and over again,
what would happen then?
Then you might be able to get something, because then you get multiple copies of each density, right? So then you can start trying to estimate.
I mean, what we did concretely, I'm not showing this here. I never brought this double pendulum downstairs because there's something hanging outside my office. We did this explicitly for this, so I can release it from the same position. And I will get all these trajectories, right? This is the optical encoded positions and timestamps. So because I can see the reading as I release it, I can be very, very confident that I'm releasing it from almost the same initial condition. So that's an independent and identically distributed chaotic experiment, right? So one of the basic things we were trying to do with this, but we kill any machine with RAM because there's so much data pouring out of the double pendulum, although it only swings for 20 seconds, maybe 30 seconds. There's so much data, so just processing all of that data, I could, for example, physicists like to look at phase densities, so they just forget about time, So for this particular initial condition, they are interested in what is the theta1 and theta2 values taken by the double pendulum before it comes to a rest. So that's a basic density of interest, right? So for that, you can definitely use this because each sample is an IID sample, and I'm ignoring the time aspect. I'm only interested in the empirical visits, and so I can reconstruct the density. So we do that in another longer paper on this. But let me give you the sort of what the construction involves, and I don't think this is the only way, but we don't know anything either way. So here is the basic same idea.
So you need to you need to connect.
Sorry.
Otherwise, we had to start our own computers and watch the YouTube stream while you're talking.
Oh yeah, true. I don't know if it's right. So this is basically I think my sort of first PhD student in New Zealand. She's in Malaysia now. So yeah, this is basically our gift to Luke.
Dedication.
Anyway, we are in this basic problem, and So the structures we study are called regular paving. So these come from data structures, computer science, even geometric group theory, and some algebra. So there's a lot of angles. So what's the basic idea? You have a box. So X, bold X is a box in D dimensions, right? Just a bunch of intervals. And then I define this funny I to be the minimum of the argmax of I, the width of I. This is basically the first smallest side of the box. Right? So, so this basically is where I split. So every time I decide to split a box for whatever reason, I split along the first widest side. And that's how I get my XL and XR. So in a picture, it's just easy to see. So here's my X row, bold X row. So this is the root node corresponding to the box it encodes. And then I get my row L and row R for the left and right sub nodes of row. And each of these nodes encode these partitions. Right? And because this was a square, this is my first coordinate and this is my second coordinate, I bisect along the first widest coordinate, which is this guy. And then I decide to split on this for some reason. Right? There's some Markov process telling me where to split. And then now this is the first widest side because it's so I split this way. Okay. So I'm X row LL and X row LR and so on. So the tree grows like this. So the point is, no matter what the dimension is, my trees will encode a partition in any dimension because I have this splitting on the first widest side rule. Right? It's one canonical rule. So these ideas are somewhat oldish, and you can ask many questions. So I think Enumerative Combinatorics, Stanley's book talks about this. Mayer's book on geometric group theory talks about this. Those guys call it finite rooted binary trees. The enumerative combinatorists, they call it, I don't know, planar binary trees, and everyone calls it something else, but it doesn't matter. So it has some nice elementary properties. So if we ask how many trees are there with k splits, it's the Catalan number. And so, here's some very basic. So from a stats point of view, what we do with these trees is so points come in to the root node. It's like the sensor. And then they start falling through the leaves of the tree. If it falls on this side, then we direct it here. If it falls on that side, we direct it here. And each node has a counter that increments as the data passes through it. So we can have other statistics like the mean and the variance covariance matrix and so on. So these are all recursively computable statistics. So you don't need to see the data. As long as it passes through it, it can update these statistics. So count is our most basic one. So we keep 10 points fell, 5 here, 2 and 3 here, right? And in the single machine implementation, we maintain pointers to these data points from the leaf nodes. And then the sort of map reducible implementation, it's done differently. So then basically you get a histogram from a partition with points in it, right? You just need the counts and the volume of each cell. That'll give you the histogram. So yeah, there's nothing more than that. So this is the algorithm on this tree space. So what we now are thinking about is some kind of a Markov chain that's running on this tree space. So think about points are fallen in one big burst. So that's our simplest scenario. So n can be some 10 million, whatever, some big number. It doesn't blow the RAM in a single machine setting. And so then I have, my root node, and then I always split into left and right. And then the question is, should I split this or should I split this? Okay. So to make these decisions, so in general, you say you come along a long way and you're in some tree, lots of splits, whatever, something like this, let's say. So then, if there are data points in some of these, let's say there are data points everywhere right now, then so then these are called splittable nodes. So then what we do is we basically arrange all the splittable nodes in some kind of priority function. So so then and then we choose the leaf node with the highest priority for the next bisection. That's the basic idea. So we have to justify this somehow. So the input to the algorithm is the initial SRP, stands for statistical regular paving with root node rho, and then X is n points, a burst of data, and then hash is just simply a priority function of counts. So this L nabla S is the set of splittable, leaf nodes, okay, of S. So I have a function that counts, that reports the number of points that fell into the splittable leaf nodes. Right? So then I have this hash overbar, which is the maximum value of the count in the splittable leaf nodes that is allowed for any splittable leaf node. So when I terminate, that is going to be my termination condition. So no leaf node can have more than hash overbar many points when the algorithm terminates. And then m overbar is the maximum number of leaves I'm going to allow in my final SRP. That also I control. Okay, so those are the inputs to the algorithm. The output is going to be a sequence of states, S0, which will be the root node, and S1 and so on. And then there is some stopping time, random stopping time, capital T, such that the set of splittable leaf nodes at the stopping time is either empty, right? There's nothing to split, or the number of points in each of these nodes is less than the upper, the maximum points allowed, hash overbar, for every leaf node that is splittable, or the size of the final tree at termination point, capital T, is already reached the maximum allowed m overbar. So that basically gives me my input and output. Right? So all I do is I initialize, and I basically dump all my data into this. And if I have domain knowledge or historical data, then I can just take the min and max on every dimension to construct a hull. I can add some buffer if I really want. Or it may be a sensor problem, like a lot of predictive maintenance problems. You know the machine's minimum and maximum, the range. So you somehow set a boundary, either empirically or with domain knowledge. That sets your root box. And then I basically start my chain with the root node, everything in my root box. And then I simply have this while loop until my termination conditions are met. I do the following. I produce a random sample from the argmax set. So this randomization is really only going to get used if two or more nodes have the largest hash. So it's nearly deterministic. Okay, so this can happen. But, so I simply produce the leaf node with the most number of points. Okay, for the next split. And then I do my split according to the first widest side, because that's a canonical partitioning rule. And I append the state that I get from the splitting, right? I update the counts and the tree keeps growing. And then I make sure that these conditions are met, otherwise I stop. So that's essentially what we call SEB tree MC, which stands for statistically equivalent block tree Markov chain. Okay, so the Markov chain on trees, and the SCB is an old idea from 40s, I think. So we're not really inventing anything here. It's the simplest consistent partitioning strategy, and all of that in this kind of generality is explained in DeVroy's other books. So our limitation to this particular tree space is our own constructive innovation, whatever you want to call it. It's not quite in Luke's book, but the SEB rule, the generalized SEB rule, these are standard procedures in a lot of the machine learning algorithms. So that's the other book on the probabilistic theory of pattern recognition. So this is the fundamental problem, the so-called smoothing problem. So if hash over bar is 50, right, I have a very different situation with very spiky histogram, right? Because this is called under smoothing. You never get under and over right. This is the over smoothing it. So here hash over bar is really big, so you don't chop enough, you know, you just under smooth, right? This is over smooth. I don't know.
No, other way around. You smooth. Under smooth means you don't smooth enough.
Okay, so I over smooth here, right? I smooth too much.
No, you want the smoother. This is too jagged.
Oh, okay. Wow, okay, I took the smoothing the other way. Okay, this is, anyway, yeah, so this is highly spiky and jagged, and this is not enough, right? So we need to find the right hash over bar. So that becomes like one of the basic parameters. So we can in fact use hash over bar itself to index our K. You know, it can act as an index if you want for the K densities, right? That we want to choose from. Because you see that Markov chain, you know, terminates after a finite point in time, right? So all the path, all the trees it visits along its path are our candidates for the K densities to choose from. It's MDE world. Okay, so yeah, so I mean, and then what we need to show is that this particular partitioning strategy is asymptotically consistent. That means as n goes to infinity, we want to show that the histogram that it constructs converges to the unknown f asymptotically, not for a fixed n part, but just asymptotically. So this requires a slightly different theory, which we didn't go to in detail, but this is a very elegant paper from 1996 by Lugosi and Nobel, right? It's the same Lugosi, yes. So what they show is that this is a very general result. It shows that for any partitioning strategy for histograms to be consistent, that means, you know, the Fn that you get from the histogram converges to F in L1 as the data points go to infinity. Then these are the three conditions that needs to be met. So the number of leaf boxes, you know, grows sublinearly in n. So as n increases, there's, you know, the number of leaf boxes cannot grow as n, they have to grow sublinearly, slower than n. And then the partition, which is you know, the partition itself for the histogram, that has to grow sub-exponentially in terms of a particular combinatorial complexity measure. So this is the VC theory for partitions. And then the volume of the leaf box and the partitions have to be shrinking ultimately. So any leaf box which has a positive through mu measure should eventually shrink to any size we specify, or smaller than any size we specify. So this is kind of the idea, and I don't want to get into this too much, but basically it's a mix of VC theory but extended over partition. So it's a slightly different deviant of VC theory. But for us, it's not too hard. The proofs. So basically, we get this result. S dot is the realized terminal state of the Markov chain, and what we can show is that the L1 distance between the unknown f and our sample-based adaptive partitioning strategy at the terminal state goes to 0 with probability 1. So yeah, I will sort of skip the proof. It's not really, it's kind of textbook proof. Okay. So, but then what is the VC part? So all of this is just to justify that we have a clever strategy, or we have asymptotically consistent partitioning strategy. But now for any fixed n, remember we really want the finite smoothness problem addressed, so we go to this MDE land. For any finite sample size n, I need to figure out where to stop, right? Because if I keep going too far, I overchop, right? So that's where we use all this entire set of lectures for today. So once again, we have so we are indexing like this. So our theta is basically going to be the number of leaves. Because as I increase the number of leaves, you know, I keep going down, right? So that's fine for my theta. And so then I also have a refinement. So because I'm splitting one leaf at below the current partition, the new one will always be a refinement of the current partition, right? Next partition will always be a refinement of the current partition. So I have some ordering there. And then what I need is my training data. So I haven't told you there is other theorems here in other chapters that get you into the world of how to actually do the estimate from endpoints. For that, we need to actually keep some of the data, hold out some of the data. And so that's our training data. So we will take some, some fraction, fee of the data that's, say 1/3 or something. And then that will form our training data. So we'll keep 2/3 as our training data and the remaining as validation data. So that's script T and script V. And and then we can call this validation data Y through V and say 1/3 of it is validation. Then for an ordered pair, theta and var theta in capital theta square. So remember, theta is just our number of leaves of each tree. So we're indexing the tree by its number of splits or leaves. So for two different splits or leaf sizes, we define our Sheffield set like this. So it's just where one guy is strictly bigger than the other guy. And these F's are the histograms based on the partition. So that's our Sheffield. And then our Yatrikos class is just a collection of all these Sheffield sets over theta, right? So we have to find an efficient representation of this Yatrikos class so that we can hunt down the delta theta directly.
I have a question.
Mm-hmm.
The Yatrikos class in this case,
yeah,
wouldn't it just be the set of cells in the finest?
Yeah.
Okay.
No, yeah, so yeah, well, in what we have is basically a vector representation that's sitting on the finest resolution where the vector keeps track of the heights of all the previous guys. Is that what you mean? Yeah, you have the finest partition.
Yeah.
That's the one below. But remember, what I'm after is think about my root partition on the very top. It's the uniform density basically on the root box. So I want to know the set of all x where that guy is strictly bigger than, say, the finest guy, right?
All right.
So I have a matrix of, so let's say with 0 splits is the root box, and m sub over bar minus 1 splits is the maximum splits I'm allowed.
No. So the thing is, you're really looking at just the densities, not just at the different partitions you see along there.
No, that's right. Yeah. So basically,
so it would be a subset of
the finest partition, yeah. Right? So I have possibly distinct, let's say m sub n over bar minus 1 square. Okay, k. Let's say k elements. K density, so it'll be k square minus k subsets of the finest partition.
Yeah,
right? Because you can think of the finest partition as lots of stuff, and there will be some histogram that's specified. But then there are all these k minus 1 other histograms that are coarsenings of this finest one, right? So each of them will have a simple function, a histogram. So what I'm really after is the set of all x where each one is bigger than the other one. Right?
So if you took all densities along the whole path, it would always be the finest one, almost surely, right? Because when you split, one side will be slightly bigger and the other slightly smaller.
Yeah, so I think we exploit all this in the actual calculations as much as possible. So the way we grow this matrix, we only do the minimal computations we need by exploiting this refinement property. So yeah, I mean, that's kind of the idea. So you hold the validation set separately, and you need to use it. So let's see. So here's kind of how you can pictorially think of it. So you have training data, which are the black dots, and the diamonds, which are the validation data, right? So about a third, say, is validation. So then you have this counters, 10 and 5 for the training and validation. So you have different counters you increment for the two. Then, yeah, to do pairwise comparison of the heights, we define these new C++ structures called collator regular pavings, or CRPs. They have their own arithmetic and stuff. So collators are collating, somehow information about what's happening. Because, the statistical regular paving just had the histogram information, right? These ones are slightly different. The CRPs, they're on the same space of trees, but I think there's a picture here. So the main theorem now is theorem 3.2. So this is basically what we've been getting into with the K stuff. So here is the sort of simple way to think about the collator regular paving. So what is it doing? I mean, this is our statistical regular paving. So it has the histogram Fn, and then the empirical validation measure. That's all this is, right? It's the two counters, right? The two counters give you the height, and this one just keeps the count, the relative frequency. So that's our statistical regular paving, and then the CRP just turns them into vectors. That's all of this. So it turns the FNS theta, the histogram height, into a vector. So this is just a vector with one element, right? That's all. So I just put parentheses here. So now the collator has this addition operation, or the union, Hull union operator, whatever, this union operation. So it will take in a SRP. So this will be the next histogram I get, and then it can collate it to the current collator, right? So you see these heights grow. That's all of this. So I have my nodes, and then I kept my original height that came from this guy I'm collating. But also what was there originally is kept as well. So I have these vectors growing now, right? So I have the heights of the previous layers kept in the nodes. Okay. So, well, that's basically it, right? I mean, that's the information I need, and then I just have to check which one's higher than which one in some clever way, and that's what we do with pointers. So given x1 through xn, the nth shadow coefficient is this is all the standard stuff we saw today. And this is basically what we derived today. And yeah, so here's the sort of performance evaluation. So we try to do it on this completely crazy density called the Rosenbrock density. So it's usually used in global optimization. So it's incredibly structured. So you can specify for any dimension, and it's this xi squared. It has this banana shape, and so we just use that, and then the standard Gaussian, and this is the sort of what it can do. So so this is all single machine. So 10 million samples, it can compute standard Gaussian in 5D and Rosenbrock in 5D. And this is my sort of L1 error. So what I'm reporting is the minimum distance estimates mean L1 error between the true density and the estimate. And I can do this because the simulation, so I know what the true density is. Right, so and then the second number is the difference between the L1 distance of my estimate to the truth and the best estimate in my class, right? So I want to know, could I, if I pick the best one in my class, which, how far is my current estimate from that one? So that's not bad. So that's, it is picking, something quite close. This is another method for comparison. So this is a MCMC method, but it's minimizing L2 error. And this takes an order of magnitude more time than the MDE method. And
sorry, can you include which situation are we in? Are we in the 1, 2, 3, or 4?
Oh, we are in the situation where F is, you know,
Was it part of?
well, F is no, it's not. In this case, F is not, you know, one of the. We're more in the scalable setting because I'm not simulating from one of the histograms.
Yeah.
F is really simulated from Gaussian and Rosenbrock, and the actual simulation program for doing it exactly from Rosenbrock is like a whole different program. So we do exact simulations from the Rosenbrock using some interval methods. So we have another paper where we do simulate from the one of the histograms itself that is closest in Hellinger distance to the true F. But we don't do that here. And the main reason we do that is because if you go, we push it to 10D, and if you push it beyond 5D, what we've done here is for the L1 errors is what's called quasi-random integration. So we use quasi-random numbers to approximate the L1 error. Those quasi-random approximations kind of break in 6 and higher dimensions. So then we don't do the simulations exactly from it. So then what we do is we find one of these simple functions in our path that is close in Hellinger distance to the true density. And then we use those functions as we simulate from them, which is just a mixture of uniforms, just because we want to do the L1 calculations precisely, because beyond 6 dimensions, I cannot get away with quasi-random. But it doesn't matter because this is all simulations. It just gives you an idea of, okay, it can produce reasonably good estimates in a very, very small time. And
what are the typical running times for doing this kind of simulation?
So let's see.
I mean, of course, it's hardware dependent.
Yeah, so I think in this one I didn't put it. Yeah, we did everything on the same machine, so I just say it's an order of magnitude faster. So I think it's. We should look at the.
The MCMC, is that a Gibbs sampler or just some other?
No, it's not a Gibbs sampler. It's actually a MCMC on the tree space, where I do Metropolis Hastings proposals and I move around. But then I take advantage of this tree arithmetic, so I can add and subtract trees with different partitions. That was the whole point of getting into this world. The whole question is how do you average 2 histograms with different partitions in any dimension, right? If you can quickly add and divide by 2 histograms with different partitions in any dimension, that's the Bayesian first step, right? Because then I can take the sample mean of a Markov chain that is moving around in the partition space, right? So people were not able to do averages for our different partitions before. So if you look at the classical Bayesian literature in this world, they always do refinements, because then they can average downstairs. But here we can. Anyway, that's so let me. So the CPU times. So the CPU times are, I don't know, you know, it's maybe in the order of minutes for this. The MCMC is literally hours, so it's at least 10 times. So anyway, this is kind of the yeah. Anyway, the algorithms are here in detail for TILO or no TILO, because you see the problem with SRP collate. You know, you have to somehow, well, the way at least we are doing this. Maybe you can think of something completely different in a distributed setting, but we are keeping track of all the heights of everyone before, right? So that we can.
Yeah, but do you use this before? Do you need this while updating? You just need the software.
No, well, the way the way the final algorithm works is we don't look at every single split, because that's incredibly crazy, right? I'll be sitting there with a huge K. So we basically.
Yeah, but do you need to know the complexity of these Yatragas classes while doing the search? You're just interested in reporting it once you're done, right?
Yeah, that's what we do. We actually just run through this, and then we go and actually compute the deltas.
Exactly. So I mean, you can still do this I mean, this all happens after the distributed part at the moment. So, I mean, what's distributed right now is just finding the finest tree. And all this happens, you can do afterward.
Oh, I see. So you want to... Well, okay,
I mean,
but then you're limited by everything being in the driver program in the end.
Yeah, the thing is that even to query the density, constructing this density estimate and storing the trees this in a distributed way, this is not very hard. But even doing a density query on if you store the tree itself in a distributed way, it's hard.
Yeah, no, that's So okay, fair enough. So if we say we limit ourselves to producing distributed algorithms such that the learned model will be driver implementable, then
yes, then this is not that hard.
That's good. All right. Well, all right. I don't have anything else basically. Thanks for everything. And